Good evening, sir.
Hello, am I audible now? Hello. Okay, great. So tell me if you face any technical difficulty at the moment you start facing it, right? So let's start our session. So in this week, what you have seen is linear maps. So these are the topics you were covered. So first of all, what is a map? Map is something that is used to transform variables, right? Right. So map basically any map is defined uh, as a mapping between input and output space. So let's say this is your input space and then this is your output space, right? So you have a map that maps each point in the input space to the points in the output space, right? So let's now talk about linear maps. So what are linear maps? So we we saw that when we do matrix multiplication, right? So when you say we have matrix M of dimension 2 cross 2 and we have a vector which is of dimensions 2, then when you do matrix vector product, you get a MV vector. This is another vector which has dimension 2 cross 1, right? So now what does this vector signify? So if you look geometrically, what it means is, so let's say this is your Cartesian plane. So initially your vector, let's say, was this V, right? Now you hit multiply the vector V with another with the matrix M, and you get another vector, let's say MV, right? So this our new vector MV, right? So now what is the meaning of MV, right? What is the meaning of multiplying M with V? With V is basically mapping this vector V to the vector MV, right? Now, for this example, what I have done is I have chosen a matrix M such that it is a rotation matrix and it is rotating the vector V by 90 degree about the z axis in the xy plane, right? So this is the Cartesian xy plane, right? This is the z axis coming outside, and then it is rotating the vector v by angle 90 degree to the vector mv. So now let's say our domain had some vector v. So our matrix m acts as a map that maps it to mv, right? And this is a one-to-one map, right? For now, let's assume, right? Now there can be many to one maps where all the vectors are transformed into zero. In that case, the vector has to lie in the null space of the matrix M, given that the matrix M is not full rank. But if the matrix is full rank, you get a one-to-one map. Fine. So this is how we look at this matrix vector product or matrix product as maps. And since we are dealing with matrix vector product, then if the matrix is constant, just pay attention to this. If the matrix is a constant matrix, then if you do matrix vector product or matrix product, you are essentially transforming lines into lines. You are either rotating the line or scaling the line or translating the whatever the line, but you are not making it non-linear. That's why these kind of maps are also known as linear maps. And this is the topic that we have seen in this week. I hope you all have gone through the video lectures, right? So just a quick confirmation: am I audible and everything is clear till now? Whatever I am speaking. Anyone please confirm by typing in the chat box. Okay, great. Thanks. Fine. So let's start.
one small one small doubt. When
Yeah, yeah.
you
What's huh?
rotate that vector v
Yeah,
around about the z-axis, so
yeah.
v and mv are in the xy plane, correct?
V and M V are in the XY plane, right? Yeah.
Thanks.
Fine.
Yes, sir.
Okay, great. So let's move further. So this was some basic introduction, what are linear maps and why we are studying these and why do we need, why are, how they are associated with the matrix vector product, right? So this is it. So Shiv Kumar, can you mute yourself because we are receiving a lot of background noise.
Yes, sir, I will.
Great, thanks. Now, so again, this was a basic example. Now let's start. Okay, let me move a few things. Fine. Right. So we saw how matrix vector product is a linear map. Now let's start with the most basic operation, linear operation that we can do. One is scaling matrices. So let's say you have an initial vector v of the length 1. Let's say this is vector v such that norm of v, sorry, such that norm of v is 1. Then let's say, yeah, if I have a scaling matrix that is scaling its magnitude by 2 times, so you get a vector, you get a vector, right? You get another vector mv, which is essentially mv is the vector is equals to 2 times vector v. So this is an example of a scaling operation, a scaling map, right? So this is one of the basic operations that you can perform by using matrices as linear maps, right? Fine. Let's move on to the next example. Rotation, right? So we already saw this example. So let's say we have a matrix M that essentially when multiplied by vector V rotates is by 90-degree about the Z axis in the XY plane, right? So whenever we define rotation, we need to define the axis around which we are going to rotate, right? So rotation, usually what we do, we perform rotation around a plane passing through the origin, right? Again, reflection also a similar operation. So in rotation, you are rotating the matrix about an axis, actually about an axis, right? And there are a few properties of rotation. That is, rotation is always commutative in 2D, but rotation is not commutated in 3D if done along separate axes, right? We will see an example on this also. So these are the two basics examples. Again, reflection is also an example of a linear map. So in reflection, what happens is you need to have a plane that passes through the origin. Then you can reflect any map, any vector across that plane in 3D space, right? So let's say this is your XYZ basis system. Now let's say you have this plane that passes through the origin and you have this vector v and you want to reflect it about the or this plane. You just take the orthogonal projection and go same amount in the downward direction, and then you get the reflected vector. So you call it reflected v, right? So this is reflection operation that also can be done using matrix vector product. Then we you saw something about a quantity. You learned about a quantity known as determinants, how it is computed. The first thing, how it is computed. The second thing, why is it useful, right? So this determinant essentially represents the volume occupied by the determinant of a matrix. Essentially represents the volume occupied by the parallel pipe formed by the three column vectors of that matrix, right? That it essentially the value of determinant is equals to scalar triple product, right? There are some properties of determinants that you saw in the lectures, and we will solve some problems such that swapping two rows of a matrix causes a determinant to get negated. Determinant of A and determinant of A transpose are same. Now, if the column of a matrix is multiplied by a scalar k, then determinant is also scaled k times. If so basically if one column you are multiplying by k, it scales by k times. If you are multiplying all the three columns by k, it becomes k cube times. For example, property 5 shows this, right? Determinant of k a is equals to k cube determinant of a. Then determinant of ab equals to determinant of a into determinant b. This can be proven, right? but determinant of A determinant in plus B is not equals to determinant of A into determinant of B. Right? In short, determinant is not a linear operator. Then determinant of A inverse equals to 1 by determinant of A. This is we will also solve this problem, right? We'll prove this. Then if two rows of a matrix are linearly dependent, then the determinant has to be 0. Why this is happening? Let's think about this during the problems, right? So just remind me to ask this question again when we solve the problem related to this. Then if the row of a matrix is 0, we get determinant equals to 0. So this was the quantity determinant that is defined over matrices, and we are seeing these properties, and we will essentially these all these properties can be extended to higher dimensional matrices also. But for our applications, we will only focus on the three-dimensional matrices, 3 by 3, right? Then what are eigenvalues and eigenvectors? So let's say you have you have matrix M, right? Matrix M has some entries M00, M01, M10, M11, right? And you have this matrix, and you have a set of vectors U belongs to R2 such that MU is equals to lambda U. What does this mean? This means the matrix M is scaling the vector U by the amount lambda, right? So what does this reveal about the matrix M? Anyone? Can you tell me what does this mean? I'm saying we have a matrix of dimensions 2 by 2, and when we have a vector U that belongs to the R2 space, right? So basically two-dimensional Cartesian plane. Then I'm saying mu equals to lambda u. What does this say about the matrix M? By this, can you infer something from matrix M? Anyone?
That that vector has been scaled. That is landed on the same one. I mean, scale. It has been scaled. U has been scaled. That
Yeah,
U vector has been scaled. That
yeah, right.
scaled or
So
maybe
the
shrink.
yeah, so u has been scaled or shrinked, whatever, right? Depending upon the value of lambda. Now, have we seen any operation like this? Any kind of matrix that this does this kind of mapping, u to lambda u? Have you seen this?
Mm, I think we have seen in scaling one also. Like
Right. That's correct. So we have seen this for scaling matrices, right? So for this to be true, you have to ensure that the matrix M is a scaling matrix. But what I am saying is it's not necessary. You can have any arbitrary matrix, then also you can find a vector U such that MU equals to lambda U. So this is always true if M is a scaling matrix, right? If M is a scaling matrix, then this is always true. You for all you will get this kind of behavior. Right. It also depends, right? There are multiple factors, but yeah, it gives some overview that this might be a scaling matrix. But what I'm saying is for any matrix, this for any matrix, even if it's a scaling or not, you can find a vector u such that mu equals to lambda u, such that is mapping a vector u to lambda u. How? So this brings us to the concept of eigenvectors, right? Eigenvectors and eigenvalues. So the thing is, let's say you have matrix A and you want to find a vector u such that au equals to lambda u. Also make sure that u is not zero, right? We don't want to ensure that u is a zero vector. If u is a zero vector, this is true for any matrix, right? All the matrices transform the zero vector to zero, that we already know. So that is not useful at all. So if u is non-zero, can we find a vector for any arbitrary matrix A such that au equals to lambda u? Can we find it? The answer is yes, and this is one of the most important concepts you will learn in linear algebra, and especially when dealing with matrices. And essentially, this concept essentially brings helps you to solve a lot of problems that you can solve using linear algebra, right? So now the problem is, can we find this? Can we solve this equation? Can we solve this a u equals to lambda u? So let's do something. Let's do some rearrangement of the equations. So I can always say a u equals to lambda u. That means AU minus lambda U into identity matrix I equals to 0. We can always say this, everyone. Do you have any doubts in this? Sorry, let me bring. Okay. AU minus lambda into identity matrix I into U equals to 0. I can always write this, right? So here I is a identity matrix, right? Identity. And right now I am not fixing the dimension of the matrix. The matrix A can be n dimensional, right? A can belong in the n cross n dimension. Then again, I has to be the identity matrix for R n cross n, right? So make sure your dimensionalities are same. Now I can always write this, right, everyone? Is this true? Is this equivalence true?
Yes, sir.
Fine, because I into U is anyway I, U, right? Identity matrix into any vector is equals to vector. It does not changes the vector. Fine. So yeah. So let's proceed from here. Now, if you take U outside and you write it like A minus lambda I into U, so you factorize it simply, and then you can say A minus lambda I into U equals to 0. Now, what are the solutions to these systems of equations? Now, we have a system of equations as that mu equals to 0. Have you seen this anywhere where U is unknown? U is unknown.
Homogeneous equation.
Right. So this is a system of homogeneous equation, right? So you want to find U such that mu equals to 0. So you set up the linear equations and try to solve the linear equations. So let's say if it's a 2 cross 2 matrix, then U is 2 cross 1. So you get two variables, two unknowns, and you solve them using these two equations from this system of equations. If it's 3 cross 3, you get three unknowns, right? So we can always solve this. Now, the trivial solution is U equals to 0, that we are not interested at all. It does not give us any useful information. Can we find a non-trivial solution, that is you find a solution such that U is not equals to 0? Yes, we can find, but there has to be some condition to this, right? Now I'm deviating a bit from here. So let me define the matrix M as A minus lambda I. Everyone please follow up this. I'm defining a matrix. Let's say that matrix M equals to A minus lambda I. Fine. So I'm defining a matrix as M A minus lambda I. M equals to A minus lambda I, right? Hmm. Then what I want to say is M into U equals to 0. What does this tells us about this equations? U is not equals to 0. U is not the 0 vector, and M, this is a homogeneous systems of equations. Obviously M is also non-zero because we are dealing with arbitrary matrices, right? This tells us one important property you need to focus on back on the thinking of the matrix M. This requires us that M must be rank deficient. Am I true? Is it true? Is this statement true? Right? If you have a matrix M, and its columns are spanning some basis, then there has to be some null space for so that a non-zero vector is mapped to 0, right? You're saying M equals to 0 such that M is non-zero and U is also non-zero. What when these conditions happen, when these things can only happen if U belongs to the null space of the matrix U. M, right? Everyone, do you agree with this or not? Yes. And U must belong to M's null space. Everyone, do you agree with this or not? If not, I can go back to some few basic concepts again.
I, I have a small doubt. What
Yeah.
is the meaning of null space?
Yeah. Fine. I hope this was covered in the class, right?
Vector space is clear. Null space, does it
Null space was not
mean
covered in the lectures.
zero vector?
So, for example, let's consider this matrix 1 0 0 1 0 0, right? This is also a matrix. Now look at its column.
1 0 0 0 1 0. Yeah.
Wait a minute, let me. Yeah. Let's say you have a matrix M that looks like 1 0 0 1 0 0, right? Now focus
Okay.
on its columns, right? So this first column is 1 0 0. This is the vector. Its second column is the vector 0 1 0, right?
Correct.
Now what space they are spanning? So this is the 1 0 0 vector, right?
Correct.
And this is
Correct.
the 0 1 0 vector, right? So they are spanning this
Correct.
xy plane that we already studied in
Correct.
coordinate geometry,
Understood.
right?
Yeah.
Now
Yeah.
let's say I
Yeah.
take a vector 0 0 1, right? We take a vector
Okay.
u as 0 0 1, right? Fine. Now what is the value of m into u? U is non-zero vector, right? The important thing is u has to be
Yeah.
non-zero. Now when you do this, you get, okay, am I doing something wrong here? E cross 2. Okay. Okay, yeah. Let me just let me just extend the matrix. I'm right. 0 0 0. Let's see this. Let's consider this matrix, right? 1 0 0 0 1 0 0 0 0, right? So all its columns are 1 0 0 0 0 0 and 0 1 0. So essentially the third column is a zero vector, right? So it's spanning this xy
Yeah.
plane. Now this
Yeah.
is a 3 cross 3 matrix. Now what is this product? This is 0, right? U is non-zero and
Yeah.
M is also not a zero vector matrix, right? All that there are some non-zero entries in matrix M. Still, you are able to find M into U equals to 0. When this happens, this is happening when the vector U lies in the null space of the column space of the matrix M, right? So these are some concept spaces associated with matrices, right? So matrix or matrices always map a vector from some space to some another space, right? That we already saw. So they act as a map from space 1 to space 2. The space 2 can be a non-zero space, the matrix column span, call span, or a null space. That is, all the vectors go to 0 if they belong to that space, right? So I just want to confirm was this covered in the lectures?
Maybe it will be in the seventh week one, because just now we have seen rotation and transformation, that part only. On week 6 only we are covering just now so
Okay,
far.
fine. So let's just okay. This is some extra detail that I gave. You can ignore this if you want, right? But this is an important detail
Thank
when
you,
you try to
sir.
understand these
It
things,
was
right?
clear. It was
Yeah,
clear in the sense when you multiply two non-zero vectors, still it can be a zero. That you are calling it a null space.
yeah. So vectors belonging to the null space of a matrix are always transformed to 0 by that matrix. That's fine. So let's ignore the null space stuff right now. Fine. So the only thing that that is important here is M must be rank deficient. That is, determinant of M has to be 0. That implies determinant of M has to be 0. So what does this mean? This means a determinant of A minus lambda I has to be 0. Fine. Now, from this, you can set up a system of equations and get the values of eigenvalues. Right? So let's consider the fixed case for 3 cross 3 matrices. So let's say I am defining my matrix as A00, A01, A02, A00, A02, A10, A11, A12, A20, A21, A22. Let's say I'm defining a vector a matrix A as like this. And now let's look at this equation, right? This is the important equation. So we can say equation 1 says that determinant of A minus lambda I equals to 0, where lambda is a scalar, I is an identity matrix, right? So let's write this. A minus lambda is, how does this look like? It looks like A00 minus lambda, A00, A01, A02, A10, A11, A12, A20, A21, A22, minus lambda into I, basically lambda into 1, 0, 0, 0, lambda into 1, 0, 0, 0, lambda into 1, right? This is lambda into identity matrix. This becomes A00 minus lambda, A01, A02, A10, A11 minus lambda, A12, A20, A21, A22 minus lambda, right? Fine. So now what I'm saying that determinant of A minus lambda I has to be 0 so that A minus lambda I is rank deficient, right? It has to be rank deficient. That means determinant of this has to be 0. Then only we can find such U, right? This is a basic property of homogeneous systems. If you want to solve the system, the matrix has to be rank deficient, right? Fine, non-trivial solutions. Then what is the determinant of A minus lambda I? You all know the formula for determinant, right? So A00 minus lambda multiplied by this into this. So yeah, this quantity multiplied by this quantity, which is A11, sorry, A11 minus lambda into A22 minus lambda minus this quantity into this quantity, right? So this is the formula for determinant that you can go look back into the lectures also. This is very simple. Minus A01 is this quantity, right? A01 multiplied by this into this. So A10 minus A22 minus lambda, right? This into this, right? A10 multiplied by this minus this quantity into this quantity, which is A20 into A12. Again, the last term plus, right? The last term is A02. A02 into this minus this into this. Let's do this. So you have something, right? A02 into some quantity, right? Now we are interested in how does this equation looks like, right? Here lambda is an unknown unknown scalar, right? So when you look at this product, you will see that this will give you a single equation in one variable, that is lambda, and this will be a polynomial and with degree 3 polynomial. So when you solve expand this and set to this 0, when you set this to 0, equate this to 0, you will see that this is a degree 3 polynomial in lambda, right? Then you can find the roots of this polynomial, of this polynomial, to get the values of lambda. Fine, everyone. So now this is it. From here you can find the possible values of lambda, and those possible values values are essentially correspond to the eigenvalues. Those are some special values associated with each matrix, and these values are known as eigenvalues of this matrix. And each eigenvalue always associates with with an eigenvector, right? So if you find eigenvalue, there has to be some eigenvector. I mean, there are always eigenvectors, but eigenvalues are always associated with them, right? For example, I was saying, right, mu equals to lambda u. So let's say there are three solutions. You can find three u1, u2, and u3. So you'll always find lambda 1, lambda 2, lambda 3, three distinct eigenvalues associated with each of them, right? So now again we have for n cross n matrix, we will get a degree n polynomial. For 3 cross 3 matrix, we have already seen that we will get degree 3 polynomial. Then what can we say about the values of lambda? And by lambda, I mean the eigenvalues. Can we use some information from polynomial root finding and use it here to identify the behavior of eigenvalues? Anyone? Can we say anything? So let's say you have a degree 3 polynomial in lambda. Let's say lambda a lambda cube plus, so let's say you get this a lambda cube plus b lambda square plus c lambda plus d equals to 0. So can we say anything about the roots of this polynomial?
Uh, we can say like all three all roots will be three all three roots will be real, or
Okay.
one real and two imaginary,
Okay.
and different case two we are not getting, other case we are not getting, I think so.
There is one more case where you get all three roots to be same, real and same roots. This
That
kind of.
only I said, it will be real, or
Hmm.
all three reals, or maybe
Hmm.
like one real and two imaginary. This two case only will get, I think.
Yeah, right. So there are three cases. So three real roots which are same, three eigenvalues, three same eigenvalues, three real and distinct eigenvalues, right? Or one real and two complex eigenvalues, right? So this is all we can say about the eigenvalues from here. Fine. Eigenvalues can be associated with multiple eigenvectors, right? For example, if you have the identity matrix 1 0 0 0 1 0 0 0 0, when you 0 0 1, when you try to find the eigenvalues of this matrix, let's look into this. Let's take a very basic example. Let's say I am trying to find the eigenvalues of the identity matrix. Right? So this minus lambda 0 0 0 lambda 0 0 lambda. This is essentially 1 minus lambda 0 0 0 1 minus lambda 0 0 0 1 minus lambda. When you find the determinant is I minus lambda I, which is equals to 1 minus lambda cube. And when you set it to 0, you get lambda equals to 1 three times. So you have three real same eigenvalues for this identity matrix. What it means is there are some vectors that when you multiply with the identity matrix, you get a scaling by amount 1, iv equals to b. Fine. So this is a very basic example. This is how you can figure out more eigenvalues for different kinds of matrices. Fine. Any doubts in the properties of eigenvalues?
So that means when same repeated eigen values are there,
Hmm.
still you have different eigenvectors.
Yeah, we can have. Yeah.
Oh, thank you.
Fine. So this was all that was covered in the classes. Now let's solve the problems. So let's start with the basic examples first. So I promised you guys that I will solve the remaining problems from the previous session first and then start with the new problems. So let me do that first. The area of the parallelogram formed by the two vectors is. So very simple example. I'm just solving this for the sake of completeness. right? There are two ways to attempt this problem. One is geometrically, one to through linear algebra. I mean, same thing there. So parallelogram is 1 comma 2. Uh, okay. Um. Okay. Fine. So this is 1 comma 2 comma 1 comma 2, right? Oh, sorry, 1 comma 1. So one vector is 1 comma 1. The other vector is 2 comma 2. So let's try to find the parallelogram and everyone. So this is the vector 1 comma 1, and then this is the vector 2 comma 2, right? Anyone, what is the area for this parallelogram?
Ze- Zero, zero.
0, right? So the because these two line vectors lie on the same line, so they enclose the area 0 area, right? You can always check this. How? We all know that for 2D matrices, area can be computed by simply by computing the determinant of the matrix, right? So what is the determinant of the matrix? 1, 2, 1. Multiple things you can do. You can always see this is a rank deficient matrix, so determinant has to be 0, or you can do the formulation. So 1 into 2 minus 1 into 2, right? 1 into 2 minus 1 into 2, 1 into 2, which is 0. So this says that the area is 0. It's a very simple problem, right? Let's move on to more interesting problem. Let the non-zero vector u equals to u1 comma u2. So we have a two-dimensional vector u with components u1 and u2. We make the following statements about the matrix u a equals to uu transpose. See how this matrix looks like. So uu transpose, right? So u1 multiplied by u1 uu transpose, right? This is essentially u1 square, u1 u2, u1 u2, u2 square, right? This is essentially u1 uu transpose. This is the matrix uu transpose. Fine. Now let's try to figure out. The question is, what can we say about the rank of the matrix and the eigenvalues, right? First, rank. We are thinking about the rank of the matrix, right? What we can do? Then select. See first. Check if it is rank deficient, right? Shant. For this, what we have to check? We have to check determinant of u transpose u, which is equals to u1 squared in sorry u1 squared into u2 squared. So u1 squared into u2 squared minus u1 u2 into u1 u2. So this is again u1 u2 squared. This is 0, right? So we can say yes, this is a rank deficient as determinant equals to 0. So statement 1. So if it's rank deficient and it's a 2 by 2 matrix, so what is the maximum rank? Maximum possible rank? Maximum possible rank is 2, since it's a 2 by 2 matrix. And I'm saying it's non-zero. It's also non-zero matrix. So minimum possible is
1.
1, right? Possible rank is 1. And since it is rank deficient, it is a rank 1 matrix. Fine. So this is a rank 1 matrix with rank 1. So statement 1 says the rank of the matrix 1 is 1. That's true, right? That's always true. That is true for this kind of matrix. Statement 2 says the rank is 2. This is wrong. Statement 2 is clearly wrong, right? Now let's move on to the next question. Next option, and has two distinct eigenvalues. Let's check about the eigenvalues. What we need to find out? We need to find out determinant of u transpose minus lambda I, which is equal to determinant of u1 squared, u1 u2, u1 u2, u2 squared minus lambda here, right? So this is u1 This is the matrix whose determinant we want to find, which is equals to, this will be equals to this into this. So u1 squared minus lambda multiplied by u2 squared minus lambda minus this into this, which is u1 u2 minus u1 into u1 u2. Now we want to find the root of this equation, so equals to 0. Just equate it to 0 and try to find the value of lambda. Okay. So let me add a page. Hmm. Now let's try to solve this. Let's try to find the equation polynomial. So this is u1 square, u2 square. Expanding everything here, and then minus u1 square lambda, u square lambda plus lambda square minus u1 u2 whole square equals to 0. Fine. Now let's make up the polynomial term here. So lambda is u1 plus u2 into lambda plus u1 squared u2 squared minus u1 squared u2 squared equals to 0, right? So these two cut and you get lambda in square minus u1 plus u2 into lambda equals to 0. Thus gives us lambda
Uh,
into, am I missing something?
yeah, it will be v1 square plus v2 square, I think so. Not v1 v2, v1 plus v2. It will be v1 square plus v2 square lambda.
Oh, yeah, yeah, thanks. This is u1. Yeah, thanks. Fine. So this is what we are getting right now, right? This gives us lambda equals to 0 or lambda equals to u1 square plus u2 square. Fine, everyone. Now, so lambda equals to 0 is one eigenvalue, and the second eigenvalue is u1 squared plus u2 squared. Now, are they distinct? Are these values distinct? So lambda equals to 0 is desirable because we already saw that the matrix was rank deficient. So we are expecting one eigenvalue to be 0. What about the other eigenvalue, right? So for the other eigenvalue, the other eigenvalue is u1 squared plus u2 squared. And since we know that u1 not equals to 0 and u2 not equals to 0, this means u1 squared plus u2 squared can't be 0. When you add two non-zero positive values, you can't get 0, right? This means, and all you can say u1 squared is positive and u2 squared is positive, right? Then you can say this implies this. Thus, this means, so let's call this equation 1, this is equation 2, and this is equation 3. 1, 2, and 3 say lambda 1 equals to 0 is not equals to lambda 2, which is equals to u1 squared plus u2 squared. So there are two distinct eigenvalues, and the matrix is rank deficient, rank 1. So do we agree with statement 1? Everyone, please confirm once. Everyone, please confirm by typing in the chat box. Everyone, is this clear? Do you have any doubts in this? Please confirm. Is this answer clear? Option A 1 is true. So statement 1 is true
So
and
it
2 is
is
false.
it starts with u1 v1 vector and
No,
v1.
no, this is U1, 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 U2. Sorry. Okay, Acha, these were U1, V1. Okay, let me just correct this. U1, UV. Let's call them U1, U2. Let's call them U1, U2. Let's not take V. U1, U2.
v1 For same
Just
U1,
forget
U2
about V.
transpose.
This is all, everything is U. So U1, U2.
Acha, okay. So in other words, the final V1 square plus V2 square will be U1 square plus U2 square.
Yeah.
Okay.
Fine, everyone. Can we proceed to the next problem? Fine. So let's move on to the next question. Prove that the determinant of a upper triangular or lower triangle. These are the problems for today's session. So we'll solve these. Okay. Let's start with the first problem for today's session. Given the reflection matrix, give the reflection matrix that reflects any vector about the plane y equals to x in the Euclidean xyz coordinate system. So let's build up this plane first. Fine. So this is the plane y equals to x, right? Fine. And we want to find the reflection matrix that reflects any vector v across about this plane, right? So how can we do this? How can we solve this problem? Let's try to solve this. Hmm. So now let's say we have a vector v and we have a plane x minus y equals to 0, right? Now can we find the orthogonal projection of this vector on this plane? Anyone? What will be this vector? This vector will be essentially replacing x and y by the quantities. So let's say v is basically v1, v2 and v3, right? So how can we find the orthogonal projection? We can always find it by y equals to x. Yeah. So we can always find it by v1 by root 2 comma v2 by root 2, right? Is this correct, everyone? Sorry. Yeah.
Like y equal to x, so it appears to be like line also, but we are taking this vector in the 3 dimension.
Yeah. So this will be
Uh,
v1 by root 2, v2
so
by root 2 comma v3.
so this will be treated as like now plane y equal to x.
Yeah.
So
Right.
we have to first find the normal vector, then only we can, I think, find the projection, I think. So the normal vector will be 1 minus 1 0. With
Yeah.
that we can take the dot product of something like that it is.
Yeah. Fine. You can do this, but you already know how to find the point, shortest point on a plane from a point, right? shortest nearest point on a plane from a point in 3D. We already know, right?
Mhm.
You can use this to get this answer, right? Am I right?
This concept I'm not understanding, like how it is.
Okay, okay.
I think we have resolved V1 and V2 along X and Y, and for Z there was no direction, so V3 will be as it is. I think maybe like that
Yeah.
it was.
Yeah, okay. So let's do one thing. Let's solve this and then.
My analysis says x minus y is equal to 0 is the plane.
Yeah, yeah, yeah.
Coefficient of x is 1, coefficient of
Hmm.
y is 1,
Y is
and
minus one.
therefore
Sorry. Huh.
the v1, v2, you can assume it as 1, 1, and the z is 0, 1, 1, 0. And then from the vector v, when you drop the perpendicular, the
Hmm.
slope of that perpendicular will be at 90 degrees to v.
Plane. Plane.
So when it is 90 degrees,
Hmm.
the what will be the slope of the perpendicular with respect to xy plane? It will be 90 degree. With respect to v, it will be
What?
the angle between the v that is perpendicular to the plane is that is 90 degree. But
Hmm.
angle of the perpendicular line with respect to the vector v is it
Okay.
45 degree?
No, 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 no. That depends purely on V, right? Let's solve this first.
Then
That
how
purely
that
depends on
root
V.
2 came, I'm asking.
Acha, yeah. Let's solve this, right? Maybe I'm
Is
wrong.
it like
So
cos 45 degree like
no,
that?
no, no, no,
Oh,
nothing. So let's do this. So we have this plane x minus y equals to 0 with normal 1 by root 2 minus 1, 1, 0, right? This is the normal. And we have a vector v is equals to v1, v2, v3 that can be written as some vector along the plane plus some vector perpendicular to the plane, right? So what is the component along the normal? Okay. So this, I think this has been covered in the class, right? So you have
Mhm.
this normal here, right? You have this normal here, fine. So in the normal direction, what is the component of V? V dot normal will be essentially minus V1, V2, comma 0 divided by root 2, 1 by root 2, right? So this is the V's component along the normal. Fine, everyone?
Uh, in the video, I think it has been explained like projection. It has been explained like u dot v upon um mod along which one we have to take mod of that into v vector, something like that. It has been
That's the
explained.
same thing, right? So you have a vector you have a vector v, and you have a normal vector n cap given as minus 1 by root 2, 1 by root 2. Then what is the component of v along the normal? You will say v dot n cap, right?
Mhm.
This is the definition of vectors dot product, right? Vector dot product. Is this true? Do you agree with this? I mean, in the
Yes.
formula, you will see that this is equal. So if you want to figure relate it to the formula, it means magnitude of V, magnitude of normal divided by magnitude of normal into magnitude of normal in the direction of normal. Am I right?
Yes.
This is the
Yes.
formula, right?
Yes. Above it will be dot v dot n.
Yeah. Minus V1 by root 2 v2 by root 2 comma 0. So now this is the component perpendicular. So we can always say v can be written as something as minus v1 by root 2 v2 by root 2 comma 0. This multiplied by normal plus some vector q such that q belongs to the space x minus y equals to 0, right? Q belongs to the space xy minus x minus y equals to 0, right? Now what is the reflection of vector v? Now this is the reflected vector v reflected. Now everyone please go back to that idea view that we were doing every time we were trying to find the reflection in the 2D space. We are simply negating the component perpendicular to the surface, right? We are, so again this reflected vector has the same projection along the plane, but its projection along the normal has been inverted, has been negated. Everyone, can you find this? Can you see this relevant information here? Is this clear? Is this information? So you remember, right? In 2D plane, we were trying to reflect this vector about the x-axis. So what we used to do, we divided this into two vectors as a sum of this vector plus the vector along the y-axis plus vector along the x-axis. Then what we did used to do, we negate the component along the y-axis and then take these two vectors to get to the reflected part. Do you remember this, everyone?
Yes.
This aspect is clear. Reflection
Hmm.
about the x-axis is clear.
Hmm. Right? So now this same concept here, instead of the x-axis, you have some plane, right? And you have its normal. Now you have some vector like this. The plane is going through the origin. Now you want to find the reflection along this plane. What you do, you represent the vector as a sum of two vectors. One vector is along normal to the surface, one is along the surface. Now what you do, you negate the component along the normal of the surface and then take the sum of these two vectors to get the reflected. Is this clear idea? Is this idea clear, everyone? Everyone, is this clear?
We have to negate which one part, sir? This I'm not
The part
understanding.
along the normal for that plane, or the part
Like
that is
normal, like
perpendicular to the plane.
normal will be minus 1 1 0.
No, normal will be unit normal. First of all, unit normal. So this will be minus 1 1 0 divided by root 2.
Okay. So which one part we have to leave now? This I'm not
Hmm.
understanding.
So let's think of this like this. So
There also it has been explained in the other way also. I think what in the classes it has been explained. Keep reflection is actually where the projection is there. So the
ah,
projection of the vector is there. Double of that minus the v vector will give the reflection point. I think it has been explained in that way in the classes.
so yeah, let's focus. Please, can you look at the screen right now? Is am
Yes,
I? Can you see my face and on the
yes, sir,
screen?
yes,
So
yes,
can you
sir,
see
Yes,
this
please.
sheet, this copy here,
yes, sir,
right? So let's say this is the plane you want to find the reflection about, right? Now let's say this is the origin, the center point on the my copy, right? This is the origin. Fine. This is the
yes,
origin. Let me mark it. So this is origin. This O is the origin, right?
yes, sir,
Now let's say from origin you have this vector. This pen is the vector, right?
yes, sir,
Now you want to find the reflection of this vector around this copy. What you do, you simply go down, right? The reflected pen is the reflected vector is this, right?
yes. Got.
This is the reflection, right?
Mm-hmm.
Now let's go back. Now this was our original vector. It can be written as a sum of two vectors. One vector is its orthogonal projection on the copy, right? On the plane. Do you agree with this?
Yes, sir.
Plus its projection on the around the normal. Fine.
Yes.
Is this clear? Do you have any doubts
Yes.
in this
No, no, no.
representation? So this
No.
plus this is this vector, right?
Yes, sir.
Now when you will observe that when you look at its reflected vector, this vector, this is again, this can be decomposed into two vectors. One is this vector, which is the projection on the plane,
Yes.
plus this vector whose component is negative, who has negative component along the normal direction, same as the component of this vector along its original normal direction. Do
Like
you agree with
here,
this?
And they
this
both will
agree.
cancel. They
Uh,
both will
Actually,
cancel.
normal vector above to that was minus 1 by root 2, 1 by
Hmm.
root 2,
Hmm.
0. So the
Hmm.
when we are going in the opposite direction, will it be 1 root 2 minus 1 root 2 and 0?
No,
No.
no, 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 no. Normal is always fixed. You have to choose a convention always.
Okay. Yes. Normal means either it is downward or upward. Will keep the same.
Yeah, as soon as you start solving a problem, you fix the normal, then you do not change throughout the entirety of the problem.
Its direction will not change. Okay, it
Not
doesn't going to
change.
affect. If I'm going to change the sign, it is not going to affect anything.
If you change the direction of normal, your computations will differ.
Okay.
Because
Okay.
let's say if you have a normal in the up pointing upwards and you have a vector like this, you will have a positive dot product. But let's say you negate the normal and then again try to take the dot product, you will get a negative dot product. So everything is changing, right?
Okay, sir.
So you have to always fix the direction of normal and then start solving the problem.
Okay, sir.
So is this clear? So was this clear?
What you explained that is clear. So let's come to that question, like how will come.
Right. So we can from here we can build up our solution, right? So if we can write this vector as a sum of two vectors, one is the vector along the surface and one is the vector along the normal. We already know the vector along the normal, which is minus v1 by root 2 comma v by root 2, v2 by root 2 comma 0. Sorry, comma v3. Yeah, this is root 2 comma v3, right? And it's this this vector along the normal direction. So into n cap. Is this clear, everyone?
Yeah, yeah.
Uh, again, I'm getting confused here. Like we have taken the projection uh, is minus v1 root 2, v2 root 2, and 0. So that will be only, I think, horizontal component. No?
Oh, okay. I have done a mistake here. Let me write this. V dot n cap, right? V dot n cap is essentially v1, v2, v3 into 1 by root 2 into minus 110. Now this is v1, v2 minus v1 by root 2. This is the component along the normal direction. Now from here you can write up the vector as a sum. So v2 minus v1 by root 2 along the normal direction n cap plus some vector q along in the plane. Now is this clear, everyone? Everyone, is this clear?
Yes, sir.
Fine. Now from here you can find q equals to v minus v2 minus v1 by root 2 into n cap, right? Now what I want to say, or reflected vector, v reflected is essentially q minus v2 minus v1 by root 2 along the direction n cap, right? Now this is the formula already you saw in the class also, if you remember. So you get this as v minus v reflected is this. Ah, this is correct. Yeah. So v minus 2 multiplied by v2 minus v1 by root 2 and cap direction. Everyone, do you agree with this? If you have any doubt, please tell me right now.
Uh, you have written two times of how we have got two times of that part. Like
Okay, from this equation, this is, let's say, your equation 1,
R reflection is equal to this I've got.
right? Now, the reflected part is, do you agree with this equation? Q minus V2 minus
Uh,
V1 by root 2 into n cap.
R reflected will be somewhere it is.
Q is its projection on the plane, right?
Mm-hmm.
So Q plus something along the normal was your original vector. I'm saying the reflected
Hmm.
vector is Q minus that thing. Now, this is correct.
Correct.
Fine, that's true.
Yes, sir.
Fine. So that is what I have written here. Now, do you agree with this?
Yes, sir.
Fine. So
Then after
now
that
what?
it is written V min.
Huh? What?
It has been written like we have substituted. I think V vector Q vector value again we have substituted. I think so.
Yeah. Now I'm again. This is correct, and from here, equation 1, I can substitute the value of Q. From
Okay.
1, I can say Q is this, and then put in the value. You get root 2 multiplied by V1 minus V2, root 2 multiplied by V2 minus V1, 0. Right? So what is this vector? And then again, we just have to figure out the map from here.
So can we do in that way also like once we'll find the projection of v vector in the plane x minus y, and from double what the foot of the perpendicular will get,
Hmm.
what vector will get over there, double of that minus v vector will give the reflection.
That's the same thing. This is again the same thing you're doing.
Mhm. We'll get same
So
result.
you will get the same result.
Okay.
I mean, what it means is, okay, so what it means is this plus this, right? Huh. So this is essentially saying this is your vector v, this is your foot of perpendicular, right? Now what you do, you double it, and when you add these two vectors, right? V or 2 into foot of perpendicular gives you the reflected vector. This is simple geometry, same thing, right? And the foot of perpendicular is essentially the v's component along the normal, and we are doing the same thing. You can see v minus 2 times v2 minus v1 by root 2 along the normal. Is the same formula, right? Can you see the resemblance? Is this clear? Can you see the resemblance between the two
Yes,
ways
sir.
we can solve this,
Yes.
right? And then 0. Oh, sorry. And then v3, right? So this is our reflected vector. Now you had original vector v, which looks like v1, v2, v3. So what is the matrix such that mv equals to v reflected? Can we figure out the matrix? So for sure, the last row has to be 0, 0, 1, and the last column, obviously. And what the matrix should look like? 1 minus root 2 v1 plus root 2 v2, right? So this into this. So 1 minus root 2 comma root 2 here, and then 1 minus root 2 v2 plus root 2 v1. So root 2 or 1 minus root 2. So this is the matrix you want. This is the answer. This will cause this reflection. Fine, everyone. Is this clear? Am I missing? Am I wrong somewhere?
And V will not come there.
What we?
V1, V2, V3,
Where?
that MV equals V reference.
Yeah.
There V you are not writing.
Uh,
I think it is
which?
M vector. It is
This is M
what
vector, right? This is the reflection vector.
M matrix.
M is M matrix. Sorry. Yeah. This is the reflection matrix. Is this right? Am I missing something? Just tell me, or we shall proceed with the next problem. Fine, everyone. Can we proceed to the next problem?
Yes, sir.
Fine. So the important thing here was how to think of the reflection along the plane passing through the origin. Question number two, find the determinant of the matrix A. So we have this matrix A given as C1, A1, where A1 is a vector, C2, A2, again a vector, and then A3, right? And let's say we want to find this determinant in terms of the determinant of, so in terms of determinant of A. So we remember from the properties of matrices, right? So if you multiply a column with a scalar, the determinant gets multiplied by that scalar. So the determinant in terms of determinant of the matrix A1, A2, and A3, right? So this is equals to determinant C1 multiplied by C2. So the answer will be C1 multiplied by C2 multiplied by determinant of A1, A2, A3. Can we prove this? Yes, we can prove this. This is a property. So this is the answer I'm giving you. Just by using the simple property of matrices. But let's see. Let's build up the matrix. A10, A20, A30, A11, A12, A21, A22, A31, A32, right? So the determinant of this matrix is essentially A10 into 1 minus A32. I think this is going to be messy here. Into A11 minus A32. Okay, the formula is wrong. A10 into A21 into A32 minus A22 into A31 minus A20 into A11 into A32 minus A12 into A31 plus A30 into A11 into A22 minus A12 into A21, right? This is the determinant of this matrix. What is the determinant of the matrix? C1 A10, C1 A11, C1 A12, C2 A20, C2 A21, C2 A22, and A30, A31, A32. This is again C1 A10 multiplied by C2 A21 A32 minus C2 A22 A31 minus C2 A20 into uh, C1 A11 A32 minus C1 A12 A31 plus C1 3 sorry, plus A30 into C1 C2 A22 minus C1 C2 A21 A22, oh sorry, yeah, C1 C2 A22 into A11 minus C1 C2 A12 A21. Now just do one thing, just take C1 and C2 as common wherever. never possible. You will get C1 into C2 into A10 into A21, A32 minus A12. Right. Acha. Minus, sorry, A22, A31, right, yeah. Minus, again take C1 out, so you get C1, C2 into A1, A20 into the same quantity, plus C1, C2 is coming out, A30 into some quantity, right? Now, when you check these quantities, these are same quantities that appear in the determinant of that matrix. So you can always safely say that, hence proven that these are same. So our result is same. So this means is equals to determinant C1 into C2 into determinant of A1, A2, and A3. Is this clear? We simply did expand the formula for determinant and you can see the property coming out to be true. Everyone, is this clear? Do you have any doubts in this? Anyone? Do you have any doubt? Please type in the chat box.
The final answer is C1
Into C2 into determinant of A1, A2, A3.
C1 C2 determinant of
C2 into determinant of this matrix.
ah
Fine?
A1 A2 A3.
Okay. Let's move on to the third problem. What is the true for eigenvalues of 3 cross 3 matrix with real entries? We already saw we get a degree, degree 3 polynomial, right? And we want to find the root of this. So we get at
At
least
least one eigenvalue real.
one real. Yeah, at least one real, right? So at most one is real. This is false because we can get all three as reals. At least one is real. Option B is true. All three are real. This is not always true. All three are complex, not even possible because they have to be in conjugate pairs. So option B is the correct option. Anyone, do you have any doubts in this? We already discussed this during the beginning of the lecture.
That please explain that B is the real answer because
Oh, because okay, so when you try to find that eigenvalues, you get up. Let's say you have some. Yeah. So do you remember where we are trying to compute the eigenvalues here? We were trying to set the determinant of a minus lambda I to be 0. Do you remember here? How we are
yes,
trying to
yes,
find the eigenvalues,
yeah,
right? Now here lambda is the unknown, and when you find the determinant of a minus lambda I and set it to 0, you get a polynomial like this. So when you expand the
okay,
formulation, you get this formula: a lambda cube plus b lambda square plus c lambda plus d equals to 0, right?
okay,
And then this is a polynomial of degree 3, and whenever we talk about a polynomial of degree 3, we can have at least, I mean, we can have one real root, two imaginary roots, which are essentially complex conjugates, or all three real roots. Do we remember this?
yeah,
So option A says at most one real. That is wrong, right? Option C, all three are real. That's not always true, and all three are complex. This is never possible. Option C is some possible in some cases, but not all. But option B says at least one eigenvalue is real. This is always true. So that's why we get to this answer. Fine.
yes.
So let's move on to the next question. What is true for the rotation matrices in 3D? Rotation operation always commutes rotation or about an axis. So what is the commutative property? So let's say you are performing two operations. You have a matrix R1 and you have matrix R2. Both belongs to R3 cross 3 space, right? And these two are rotation matrices, right? These are rotation matrices. Now the question is, they are commutative with R1, R2 equals to R2, R1. Is this true? Anyone? Is this true for
Just
any
now
matrix?
you have explained it will be true in two dimension and three dimension. It is not going to satisfy.
Right.
I
So
think.
for any arbitrary matrix, this is never true. I mean, this is true in some cases, but this is not always true for arbitrary matrices. But for special matrices such as uh, rotation matrices, we can find this property to be true for certain cases, right? So let's think of it geometrically instead of getting into the details of how rotation matrices look. Now let's say we have this 3D space. This is the x-axis, this is the y-axis, and this is the z-axis, right? Now, let's say you have a vector v that looks like this. So let me take the black pen here. Now this is the vector v. You rotate it by angle theta about the z-axis. So about the z-axis in the xy plane, and always we are doing rotations, let's say in counterclockwise. Always counterclockwise, right? So it rotates by angle theta at it at and it becomes this vector v reflected, right? So let's call this r1v, and this is the angle theta 1. Let's call this theta 1 about the z axis. Now what you do, this is r1 rotation 1. This is rotation 1. Now for rotation 2, you rotate by angle theta 2 about the x axis in the YZ plane and counterclockwise direction again, right? So what will be the counterclockwise direction? Okay, right. So what is the counterclockwise direction? Um, Again, let me take the color, new color here. So now in the this is theta 2 again. So now you are counterclockwise, you are moving in the counterclockwise direction in the YZ plane. The x axis is fixed. So you go from here to here, right? And you get to this vector in the xz plane, and let's call this r2 r1 p, and this is angle theta 2, right? This is one thing that we are going to do, one operation. Now what is r2 r2 r1, right? This is x y and this is z plane. Again our vector looked like this was our vector v, right? Now what you do, you rotate by angle r2, rotate with the matrix r2 by angle theta 2 along the axis x in counterclockwise, right? So you rotate about the x-axis in the YZ plane. So it rotates from here, it comes from here to here by angle theta 2, it becomes this vector, right? R2v. Now the second rotation is R1 theta 1 about Z in clockwise, right? Let's do this. So you rotate counterclockwise in the XY plane. So this becomes, sorry, this becomes this vector. This is angle theta 1, and the final vector looks like this v. So r1 r2 v, right? So now can you see r2 r1 r2 v, right? So you can see r1 into r2 into v is not equals to r2 into r1 v. Everyone, do you agree with this? Just looking at this geometrically. Do you agree with this? It might get a bit confusing in the figure on a 2D surface on the page, but you can always think of it in the 3D space. Let's say you rotate like this and then this, or you rotate this and then this and then this. So these two are not same. So you cannot very quickly check in the 3D space that this is not true always. If the axes are different, right? But let's say if you're doing this rotation along the fixed, if R1, so second case is R1, R2 are done along a fixed basis, let's say x-axis, then is this true? This is always true. So this is vector 1, you rotate by angle theta. So no, let's take z-axis so that the visualization is easy. This is x, this is y, right? Now let's rotate by angle theta 1 here. You get this vector, and then rotate by angle theta 2 here, you get this vector, right? You do the same thing here. Here, for both rotations, I have fixed the basis, fixed the axis around which we are rotating. This is vector V. You rotate by angle theta 2, right? So you get here, and then you rotate by theta 1. Theta 1. In both cases, you get the same result. In this case, you can say R2 R1 equals to R1 R2. So it commutes only if the axis of rotation is fixed. If it's not, then it does not commute. You can always try this in 3D by taking example and always taking a vectors. So everyone, do you agree with this observations? Everyone?
That means the order of rotation can be interchanged.
Huh.
That is, first you rotate R1 for an angle theta 1, and then rotate R2 for an angle theta 2 about the same axis.
Yeah.
Then it ends up with the same vector.
Yeah, then order does not matter. It commutes. But if there are two different bases axes around which you are rotating, for example, first along the x-axis, then along the z-axis, then the order is important.
Okay.
Everyone, do you agree with this? Do you have any doubts in this?
So now the rotation operation always commutes is not correct. Rotation about an axis always commutes. That would be correct.
Correct.
Rotation
And
about
about
two axis always commutes, also wrong.
ha,
Rotation operation never commutes is wrong. So a correct answer would be B. Am I right?
option B, yeah.
Oh, okay. Thank you.
Satinder, do you have any doubts? You are saying yes and no at the same time.
Actually, before you have asked any doubt, I said just now you have said no. Any doubt? I said no, sir.
Okay, okay, fine.
And
So let's
before
move
you
on
have
to the
asked
next.
things are
Uh,
clear or not, so I've written yes, sir.
okay. So let's move on to the next question. For the vectors in 3D space, which of the following is not true? Fine. Looking at the options, one thing we all can agree on that these are scalar triple products between three vectors, right? Everyone, do you agree with this?
It's not true, meaning false. No.
What?
The question is not true,
Yeah,
false. So A
yeah,
dot of B cross C.
right. So let's take these three vectors, right? A, B, C in the 3D space. The first option says A dot B cross C. First, let's start with one thing. What is A B cross C here? Let's try to solve the thing in the parenthesis first. So B cross C will go like this, right? So it will use the right hand thumb rule, right? So you put your thumb perpendicular to the plane of BC, right? So this is the BC plane. So you put the plane, your thumb perpendicular to this plane, and then you rotate your fingers from B towards C, right? So the answer B cross C lies in this direction. So let me do this. So this is, let's say, B cross C. Then what is so this is A, what is A dot B cross C? A dot B cross C is this some scalar quantity which is positive, right? Now this says, and what is essentially this? This is the volume of the parallel pipe formed by these three vectors, right? So you can always extend these vectors to form a parallelopipe, right? So this is your parallelopipe that you will obtain when you extend these vectors, right? So this is the volume of this parallelopipe, right? Now what is B dot C cross A? Again, so okay, let me do this. So you already have seen this as scalar triple product in the lectures, but again, let me. Fine. So this was your B cross C vector, right? This was perpendicular to this plane. Now again, let's use the same vectors here. Fine. So let me. Fine. So this was our original setup. The option A says B dot C cross A, right? So what is C cross A? It's a vector perpendicular to the plane of C and A. The plane of CA looks like this. The perpendicular will be in this direction. And again, go from C towards A, right? Right hand thumb rule. So go from here to here. So your vector has to lie in this direction, right? Sorry. So this will be the vector that will be perpendicular to this plane, and this is C cross A vector. So this is some quantity B dot C cross A, which is positive, right? At least by sign we can say these are same, but by geometry you can always find out that this is the volume of the parallel pipe formed by these three vectors. So this is true. So this is equation is true. This is true. You can simply write down three vectors: a1 a2 a3 b1 b2 b3 c1 c2 c3, and write the left and right hand side. You will find that they are same. Option B, B dot C cross A is equals to C dot, okay, A, B, C. It says B, C, A, and then C, A, B. Again, option B will be true. You can always think geometrically like this also, or you can expand it and find out, right? Option C, B, A, C, and A, B, C. Yeah, option C is also correct. Also true. Option C will also be true. Option D will be false. So the correct option is option D. How did I reach here? The first thing that you should do is try to write the equations and figure out what it means. Geometrically, you can always see this says you have vector A, vector B, vector C. What is the volume of this parallel pipe, right? And then you have a vector AC, ABC, right? So whenever you think of the parallel pipe, you will get the correct answer, right? But when you think of this last option, it says A dot B cross C is equals to A dot C cross A. Now this not this can't be zero. It not necessarily is zero, but this RHS is always zero. This is always zero, always. Why? Because C cross A is perpendicular to A and A dot something perpendicular to A has to be. Fine, everyone? Do you agree with this? This is a very simple observation. C cross A is perpendicular to A and A dot C cross A has to be zero. Everyone, do you agree with this? Fine. Anyone, do you have any doubts, or we can move on to the next question?
So whenever you take dot products, angle between those two vectors should not be zero.
No, no, no. When you take the dot product and if the angle between the two vectors is 90°, then the dot product is zero, right?
Oh, the cos theta, yeah. Understood.
Fine. Yeah. So let's move on to the next question then. I think, yeah, this is the last question that I'll be covering today. The eigenvalues of the matrix X are, again, you need to set that form a polynomial, that is also known as characteristic polynomial, determinant of Ax minus lambda I. Lambda I has to be zero. Let's find this. So the matrix X minus lambda I is 1 minus lambda 0 1 0 1 minus lambda 0. Sorry, here it is 2 1 and 2 minus lambda. What is the determinant of this matrix? This will be 1 minus lambda into 1 minus lambda times 2 minus lambda minus 0. Fine. Minus 0 into something is always 0, plus 1 into 0 minus this. So lambda minus 1 into 2, right? So this is equals to lambda minus 1 squared into 2 minus lambda plus 2 into lambda minus 1 equals to 0. Lambda minus 1 is common here, and you get 2 minus lambda minus 1 into lambda minus 2, right? This has to be set to 0. The one eigenvalue is lambda equals to 1, right? And the second eigenvalue can be found by solving this quadratic. So this quadratic says 2 minus lambda square. So lambda square minus 2 lambda minus 3 lambda plus 2 plus to 0. Let's solve this quadratic. Minus lambda square plus 3 lambda equals to 0. So this gives us lambda into 3 minus lambda equals to 0. So lambda equals to 0 and lambda equals to 3. So the three eigenvalues are lambda equals to 0, 1 and 3. This was a very simple problem. You just need to figure out how to find the characteristic polynomial, right? If you are able to write down the characteristic polynomial, this is the characteristic polynomial, right? You can find the roots of that polynomial. Is this clear, everyone?
Uh, excuse me, sir.
Yeah.
Like what the matrix we have for which we are finding this lambda value,
Yeah.
eigenvalues.
Hmm.
So if that determinant of that matrix is coming out to be zero, it
Yeah.
means ki one of the eigenvalue definitely will be zero.
Yeah. Yeah.
So can't we convert like that 3 cross 3 if determinant is coming out to be 0, so
Hmm.
can we convert into 2 cross 2 we can transform that part rank deficient, and then we can find
No, you
eigenvector again.
can't. You can't figure out a 2 cross 2 matrix always, but you can
Oh,
always figure out a 3 cross 3 matrix with one of the rows or one of the columns to be zero, not
so
both.
okay, one is if the matrix like the determinant is coming out to be 0, so now
Yeah.
we are confirmed that one of the value of the lambda is 0.
Ah.
So can we come to the answer directly to 1 and 3 by some way, like instead of expanding, I'm thinking of like if it is like more dimensional
If you
than
can, if you can convert it into a diagonal form somehow, if you can transform it into a diagonal matrix,
okay,
then you can come to this.
okay. Otherwise, like we have got the equation in the beginning only.
Hmm.
I think one of the root is lambda 1 is 0, so
Hmm.
maybe that converts into quadratic, I think so. Uh,
Yeah,
above
you can
equation.
always do that, huh? I mean, if you want to solve a 3-degree polynomial, there is many way to solve this,
Okay,
but
okay.
getting to the answer directly is not possible. You can
Mm,
form some upper triangular form of this matrix, and then you can use the properties of triangular matrices also to do this, but not directly.
okay, okay. Thank you.
Fine. So question 7 was covered, question 8 was covered, right? Question 9 again, question 9 and 10 are interesting problems. So should we cover this in the next session? It's already 8 p.m. here.
We'll do it in the next session because here there is no power. Sitting in the dark, actually, only laptop has the power.
Okay, okay, fine. So let's cover these problems in the next session. It's already 8. So thank you all. So let's meet in the
Yeah,
next week.
yeah. Thank you very much.